explore Earth. You have not really an idea what's out there. You know Earth, and you hope Earth is out there, right? So basically it's like Columbus. He was like, he knew, well, Europe, and he said, well, Europe could be out there, or China. He actually wanted to go to China, but... So what we're trying to do is have a look at us, and then say, what about if we wouldn't orbit the sun? What about if we orbit a star that's actually cooler or hotter? What would that change in the types of spectral fingerprint that we can look for? And then what about if we actually closer to our star or further away? Of course, you don't want to run into being Mars or Venus, because that would be kind of bad for us. But you have a bit of wiggle room. You know, you don't go all the way to Venus because that's too hot. You don't go all the way to Mars because we know that's too cold. But in between, what about if you shift the planet around? And then what about if we are not there yet? What about this planet only has bacteria? What about if it has dinosaurs? Would it look any different? Would we actually be able to tell? So to show you again, and I don't want to bore you with that, this is the fingerprint of our planet. It's a mission that went to Mars, looked around at our planet. The black line here is the data, and the red line here is the models. Because if you start to model things that are different from yours, what you really want to make sure is that you know and understand that your model works. What about if you have a look at the optical, so where we see? How do we actually do that? Well, we have Earth, and we have loads of satellites around us, like they fly and they have a look at the Earth. But the problem we have there is that they only look at patches of the Earth. They're a few kilometers wide when they scan the sky, when they scan the surface. So what you can actually do to see this planet, because it's far, far, far away, it's only going to be one dot, nothing else, no resolution, no continents, no water. So what we do is we actually, the light shines onto our Earth, right? And then the Earth reflects back into space. Part of that reflection gets impinged on the moon and then actually reflected back to us again. And this is what we collect. So it's kind of weird, but basically the sun shines on the Earth reflects off to the dark side of the moon, so the side that's not lit, and this gets reflected back to California and France. There's the two groups who are doing this. And this is what we then collect, because that mimics our planet being just one pixel, being just a tiny, tiny dot. And this is the data that we get out of. And here again you see the features for water, for oxygen, this steep line here. And then here, this increase, this peak here, is what tells you that there's vegetation on this planet. Of course, the problem is we know that there's vegetation on our planet. And we know how much vegetation we see. So for a planet that we don't know, where we don't know what vegetation is out there, finding a feature like this for vegetation and chlorophyll is going to be very, very tricky. Just keep that in mind if anybody tells you that they can tell you something about it. Well, Earth, we are part of the puzzle. What about us? What about if we have a look at our planet through time? We go through what we call the habitable zone. This is the nice region around the star where you can have water at the surface. And then what about if the sun is not as bright? What about if the sun is brighter? How would that change us? And just in light of the recent developments, what about if our planet were actually bigger? Would that make a big difference? Like if we're 5 times our size, would that be a problem or not? I usually think about this as 3 axes, but I already have a 4th, so the 4th is either there or there. I have to basically increase my graphical arts schemes. But what I wanted to show you is like, this is us. Our sun is a G-star. And this is our planets, right? This is Earth. Venus is too close to the star, so the blue thing here indicates the zone where we think that life could actually evolve on a planet, if it's a planet like ours. Again, if it's a planet like Mars, it's too small to keep its atmosphere, so it's too cold there. So if we move Earth a bit further out and a bit further in, not to Venus orbit, but a bit closer to Venus and a bit closer out, what we find is that we have a habitable zone that's more like a Goldilocks zone. So what happens if I move Earth closer to the sun, what I start to do right now is I actually start to boil off all the oceans. It's nothing like a Boston summer day, it's way worse. So it just keeps boiling and boiling and boiling until there's no water left. So you don't want to go there if you can help it. And then what happens if you go actually to the site where Mars is? Then it just starts to freeze. Boston winter, just there forever. We go into an ice age. We start to have more clouds. But basically we can see that in the spectral fingerprint. And this is a lot of lines, so don't worry about it. But the green thing is us. Again, you see CO2 here, you see ozone here, and here is water, and here's also water.
Is this based on the Earth's size being constant?
This is now based on the Earth size being constant. I'll show you later.
You can go larger.
I completely agree.
And hotter.
Yes.
And go out to Mars and beyond and still maintain a habitable condition.
I completely agree. So I'll show you that
So
later.
what depends on the internal temperature?
It all depends on the internal temperature, on how heavy the planet is, so how much atmosphere it can keep, even if there's like things boiling off. I completely agree. But so we basically started with exactly the Earth. We move it around, then the Earth around different stars, and then we started to make, what about if it gets bigger? What about if it gets smaller? So this is exactly our Earth. And we just moved it, that blue line is moved towards the star. And here you don't see many features at all anymore, because you only have water in the atmosphere. It's a steam atmosphere. It's like if you go to a sauna, into a steam house, that's what Earth looks like. And then if you go further out, you see that you have more and more CO2 in the atmosphere, because this is how the Earth tries to compensate and keep the atmosphere actually warm. But so we have generated a kind of fingerprint for our Earth, exactly our Earth, moving it closer and further away. So if we find a planet and we make a fingerprint, we should be able to say if this is a habitable planet close into a star or farther away from a star. Then what about if I move it around different stars? Well, this is us again. So it's our star, our sun. And then you have a smaller star. And here what you see, what happens is you still see water, you still see ozone, and you still see CO2. So basically the fingerprint remains intact. Even so, of course, the planet has to be closer to the star to keep warm. What about if the stars get actually brighter? So if it's an F star, its temperature is higher than our sun. And here you see where things start to get funny. You see the CO2 feature and you see the water feature. But you don't see them very nicely separated anymore. You still can find them, but they start to blend. Here's another water feature. And what you also see is that the ozone feature starts to go away. It doesn't go away because we don't have ozone anymore. It goes away because the star itself has a different UV. So the ultraviolet that we shield again, the F star is different. So it doesn't actually show us that much ozone anymore in the atmosphere. We will not see it. But still, if it's reasonably close to the star like our sun, the fingerprint of carbon, water, and ozone should be good to indicate whether this is a habitable condition. And then we were talking about I was talking about the new planet they found. Well, the new planet is about a really, really tiny star, a very, very cold star. So it has to be very, very close. And trust the editors of the journal to actually think about how to indicate that. Because this, honestly, is a tad too close. If you're this happy people in it, and there's actually a part of a protuberance, like a part of a flare from the star that finds it in your path, you're probably not going to be a happy planet for any longer. So we were trying to tell them that. We're like, no, not there. You know, over here maybe, but not. And especially not into this. But they were like, no.